So now we can understand why the curve looks the way it looks. Right? And the y value is called the probability density function. So is PDF a probability or not? Then here is the answer. Technical answer, not a probability. However, I won't say non-technical, but a accurate but approximate estimate. Accurate and approximate estimate. How do I make sense of that? But an approximate estimate, which is very reasonable, is to say that the larger the PDF, the higher the value, the higher is the chance for it to happen. Why do we say that when we say it is not probability? Well, think of it as a very tiny little strip. It is not zero width, it's got a little bit of width, and therefore the taller the y value, the larger the area, don't you think? If we fix the width as a tiny little width like 0.0001 unit, then the larger the PDF, the larger the area. And area is the probability. Area under the PDF is the probability, right? So even though the y value itself on a particular x value, the 1 point, has no area, and that's why we say PDF is not probability. In our mathematical modeling, we also frequently say, well, here the most likely value for x is 1. Why? Well, because it's tallest. You might have heard such discussion before. And that discussion, while technically is not complete, because what the author is trying to think of is, if you imagine a tiny little strip of width, all right, then should we not agree that the taller the PDF, the larger the area, than a comparable little width? I exaggerated the width. It should be very tiny, right? That is somewhere else, and that's of lower height. So the taller the PDF, the higher the value for PDF, the larger the area. But the larger the area, the higher the probability. Yeah, so it's a long mouthful of words. That's why sometimes we cut short that reasoning by simply saying, oh, because PDF is very high here, so the probability of X being 1 is very high. So it is not strictly technically right, but it is after that inference correct to say that. So it's not wrong, you can actually prove it. But so long as you think of it as a tiny little narrow strip rather than a stick, a sort of widthless stick, then it's not correct. But tiny little width is correct. So what if the width is 0? If the width is 0, then we are talking about a point, right? Like the x-axis being fixed at point number 2. At point number 2, what is the area under the curve, under the PDF? Then the area is 0. The area is 0, correct? Because it's height times width, and width is 0. Therefore, I don't need to worry about the height. So probability is 0. But that also means that any point doesn't have to be 2. Can be 3, can be 3.5, can be 4.92. Any point, if you ask me, what's the probability of x equal to 5.13? 0. Probability of x equals to 0.34, 1.54, 0. So probability of x taking any point value is 0. You need to wrap your head around this, right? Okay, so how can it be that the probability of x at any point is 0, but then with all the infinitely many points, there's an area, right? So this is true nevertheless, and that is a pretty profound question that we shouldn't need to discuss here. But to solve your homework exercises correctly and to answer your exam questions correctly, you must absorb this point, this fact actually, that when p of x equals to any particular real number, answer, what's the probability? Answer is 0. But the probability of x within any range is not necessarily 0, depending on the PDF. Okay, so let's try to solve this question. What's the probability of x between 1 and 2 for this yellow curve distribution? And the solution is already seen here is 0.5. Why? Because we integrate it. We need to count the area. That's right. You can imagine that there are many little balls all filled up, and then you start counting the balls, right? And you sort or discs for that matter, and then you sort of calculate the unit disk area multiplied by number of little discs that you can stuff inside. So we did that as an example in our introductory video when we talk about estimating the area of a circular patch on the beach, right? If we know the area of sand, one piece of sand, so we need to count the sand and then multiply by the area of the sand. So likewise here, although one can imagine that the discs, there'll be little hollows in between them that wouldn't be fully counted. So to make the whole thing work, the technique is called integration. So the integration will really count every single particle occurring from 1 to 2. And that will be exactly right. And that's the integration part. So we will deploy this tool and say, let's integrate the PDF. Okay, so to calculate the area, we want to integrate the area under the curve from 1 to 2. And that is integrate from 1 to 2, the PDF. The PDF is 1 over x squared, but the x is actually the x-axis. So we just replace with another dummy variable. It can be u, it can be v, it can be w, it can be s, so I just use u conveniently. So 1 over u square, wherever there's an x, replace with a u. 1 over u square du. That means we will integrate with respect to u and ignore any other labels that may be around, like a over u square will ignore a or other letters. So the integration of this can be easily looked up from tables if you cannot recall. And not being able to recall the integrated form is okay, not to worry, because we're here to learn about statistics and probability. And we're not here to be tested on calculus. So you shouldn't need to worry about not being able to memorize all the integral formulas, and that is actually not called for. So don't worry about that. What you do have to know, however, is that when you have a PDF, and in that case, you have a continuous probability distribution, and you need to find the probability, then of course you must know that you have to integrate the area under the curve. Okay, so we do that, and 1 over u squared, the integrated form is minus 1 over u. Okay, and then we need to substitute 2 into wherever u occurs, minus another copy of it, and then replace any copies of u with 1. So 1 copy of minus 1 over u, another copy of minus 1 over u. The first one we substitute with the top number. This is a must. The second one we substitute with the bottom number. And then we simplify it and we get half from that. Very simple. Okay. Now, you might also be very visually attracted to this outline here, which encapsulates the area that we want to find, isn't it? And doesn't this look like a trapezium? Isn't it? Yeah. So if we have an explicit area for the trapezium, can we not just use that? And answer is yes. Yes. All right. What's the area of trapezium? If I recall my trapezium formula correctly, is half of the 2 parallel sides, right? So now the parallel sides happen to be the y values. So one side is 1 unit, the other side is a quarter unit, 1 over 4. All right. And then, so the average of the parallel sides times the height or the width, which is 1. So we can just times 1 here. So we will have basically 5 over 4 and 5 over 8. All right. So that's going to be basically 0.5 plus 125. So that's 0.625. 0.625. Okay. Now that is an approximation, so it's kind of overshot. We know the real actual answer is 0.5, and we know it's exceeding because our line here included this tiny little white patch here that is extra, right, to the yellow area. So we know that there will be a bit of excess rather than lack of it. So we know our answer will exceed the correct answer by a bit. By how much we don't know, but so the answer here is 0.625. But that's an approximation, not too bad. And although it's not accurate, it's giving us the correct idea. So what if we have a PDF that is a straight line between 1 to 2, and then from 2 onwards curves downwards? Then this part will be exactly the correct answer. So we can always create very arbitrary PDF functions by saying 1 to 2, it is a straight line. 2 onwards, it is 1 over x squared, So why not? Yeah. So it is entirely possible. So long as the PDF follows two properties that are kind of mirror images of the two properties in discrete probability distributions.